Hello, this is Kan-Lin speaking. I'm from National United University, Department of Energy Engineering. And in previous, we've been talking about the flow rate for a given output current. You can, from the Faradays law, you can calculate the mass flow rate, molar flow rate, or the volumetric flow rate of the reactant or the product. And those number is a theoretical calculate. You had to based on you had to consider in reality. You had to calculate the stoichiometric ratio defined by the test station or by you or the operating mode. You had to consider those parameters, so you determine how much flow rate. And in this section, we talk about 1 kilowatt stack, and based on how we calculate the flow rate. And just give an exercise. So, what is the hydrogen flow rate is required to generate 1 kilowatt power? So we already know, but over here we assume the cell output voltage is 0.7 volt for a single cell. So the power P equal to the E times I. The E is a cell voltage output, cell voltage times the cell output current. I. For a single cell, if this is single cell for 1 kilowatt, which is usually impossible, not likely to generate 1 kilowatt, but we do the calculation anyway. So the output current from there is equal to I equal to P divided by E cell. That means 1,000 watt divided 0.7 volt equal to 1,429 amp. So from there, we know the output current, so we can calculate the molar flow rate or the from the previous this equation. So we substitute the number in there, we can calculate. We need about 0.0074 mole of hydrogen per second, able to generate 1,429 amps for a single cell. If this output power is a stack with N cell, what will happen? Actually, we still had to calculate the current, how much current will go through the stack. So over here, the I equal to P divided by N and the E. The N is the number of cells. Over here is 20. So the total output voltage inside the 0.7 volt. Right now is 0.7 times 20 is 14 volt. The output stack voltage. So the output current will be 71.4 amps. So the number of the hydrogen molar flow rate required, the same equation, we put the number in there, crunch it. It will end up with a similar number with a single cell. You can see for the single cell, this volumetric flow rate for a stack, they will be the same. So the volumetric flow rate of the hydrogen, you can calculate by molar flow rate times the molar volume, 23.65. And then the 60 seconds per minute is just unit conversion, convert into the liter per minute. That's it. So you end up, this is a hydrogen flow rate for 1 kilowatt. That's about 10 liter per minute. If the hydrogen utilization rate is 0.8, then we need to divide by 0.8. So you end up with 13.1 SLMP per kilowatt. This is at the cell voltage 0.7 volt, and the utilization rate is 0.8. If this number change, of course, the volumetric flow rate also will change. Then how about the oxygen? If the oxygen utilization rate is 0.2, that means stoichiometric number is 5. Then what will happen? The hydrogen, this volumetric flow rate, and this oxygen volumetric flow rate is half of the oxygen, because hydrogen, each molar of hydrogen will be generate 2 mole of electron, but each mole of oxygen will generate 4 mole of electron. So volumetric flow rate with the same output current or power, the oxygen requirement is half of the hydrogen. So this is the oxygen volumetric flow rate. Since the utilization rate is 0.2, or the stoichiometric ratio is 5, so you need to divide by 0.2. You can get the actually volumetric flow rate for the oxygen. For the air, the oxygen only 21%, so you need to divide by 0.21. You can get actually air flow rate. So this is a condition at a 0.7 volt, 0.2 utilization rate. You can have the air volumetric flow rate is at 125 liter per minute per kilowatt of the fuel cell output power.